Good morning. How are you doing today? I am doing well. Thanks for asking. Partial fractions. Today, we're going to go over partial fractions. So the idea with partial fractions is a lot of times back in the algebra, you would combine two separate fractions into one fraction. And that is considered simplifying. Well, it's kind of ambiguous in life. What's actually simpler? And so for a lot of integration, it's easier to have them separated, to decompose the fractions, if you will. And it's not always entirely intuitive how to do that. So this is really an advanced algebra type thing more than a calculus thing. But since this is only really useful for integrals, you probably no one ever taught this to you. And so that's why traditionally you'll go over partial fractions in calculus. So a couple of, rules. It's similar to trig substitution in where it's like, well, we'll take this random guess and then do some algebra and things work out magically. The only real difference here is it's much simpler. And the guesses seem more intuitive. So I'm going to write down some of the guesses real quick. So if you see something along the lines of 1 over ax plus b, you should guess that the solution will be something along the lines of a over ax plus b. You're like, what? That doesn't even... Bear with me here. Follow it. If you see something like 1 over ax plus b to the k, you should guess a over ax plus b plus, scooch over, create a little more real estate, b ax plus b squared, and then continue on with higher and higher exponents until you get ax plus b to the k. And the z there doesn't imply there's 26 of them, but it's just there as a placeholder for some further letter down the line. And then, if you get something along the lines of ax squared plus bx plus c, you should guess that this is something like ax plus b over ax squared plus bx plus c. And your thought might be, well, what if it doesn't reduce down to quadratic? All the problems that you'll be given will reduce down to quadratic or a single power polynomial. Yep. And then one other thing, if the order of the numerator is higher than the order of the denominator, you should divide one by the other. So I think that's called like an improper fraction. So if you have something like x squared, let's say 3x squared plus 2 over x squared, then you should divide one by the other one. So, or x cubed over x squared, x to the fourth over x, or just x squared over 2x squared. So what you're concerned about is the exponent on the x's. And that's what would give you the order of your polynomial. Okay? So you got kind of a general feel for these rules. I'll leave most of these up here. Delete some of the riffraff. And then we'll grab an example and carry on smartly. Okay, first example. So we have 4x squared over x minus 1 times quantity, x minus 2 quantity squared. And your first thought might be, okay, so we have a higher order in the top than the bottom because we have an x squared right here, and then all we have are x's. That's not the way the rule works. If you multiply this out, you'd get x cubed on the bottom and then x squared on the top. And that's what I mean by the rule with dividing the numerator by the denominator. So the way we would start with this one is, I think I'll stick with orange. Everyone likes orange. Okay, so we'd have x minus 1 at the bottom, so we'd write a equals x minus 1 plus b over x minus 2 plus c over x minus 2 squared. And now what we're going to do is we're going to find a, b, and c. And so the first thing we're going to do, I guess second now since we've already done something, plus we check for which rule, so this is probably closer to third, we're going to combine them into one fraction again. So for the a, we're going to have to multiply that by x minus 2 squared. And then for the b, we're going to have to multiply that by x minus 1 and an x minus 2. And then for the c, we'll multiply that by x minus 1. And this will all be over x minus 1 times x minus 2 squared, which is the same as we have over here. And so now it becomes maybe not obvious, but at least possible to see that this part up here is equal to 4x squared. So we're going to multiply things out. So we have a, this is big, x squared minus 4x plus 4. That's the FOIL method. First, outer, inner, last. I just say that because I just multiply everything by each other. Don't actually understand what the foiling means. Okay, minus 3x plus 2 plus cx minus c. Okay, then I'm going to rewrite it again. And let's see, we'll separate out x squared, so I'll have x squared times a plus b plus x times c minus 4a minus 3b. Seems reasonable. Plus 1, which is kind of like x to the 0. 4a plus 2b minus c. Okay, and now we use this portion right up here. So we know that a plus b has to equal 4. Because we need to get 4x squared somehow. All we have is a and b interacting with x squared, so a plus b has to equal 4. We have, I'm going to rewrite this part slightly. Oop, you can go away, get out the purple, plus 0x squared, no, plus 0x plus 0. That way it's a little bit more obvious than that we have c minus 4a minus 3b equals 0. And then we have 4a plus 2b minus c equals 0. So first thing I'm going to do is I'm going to rewrite these a little bit. So I'm going to say c equals 4a minus 3b, and c equals 4a plus 2b. No, this should be plus 2b. And it looks like these two equations are the same, so we can set them equal to each other. 4a plus 3b equals 4a plus 2b. Cancel the a's. 3b equals 2b. Cancel the b's, and we have 3 equals 2, which is not possible. So the reason we got that crazy answer of 3 minus 2 was because the only way this is true is if b equals 0. So we know b equals 0. Come back up here. We know then that a equals 4. And so we have c minus 4 times 4 minus 0 equals 0. C minus 16 equals 0. C equals 16. Okay, so now we know A, B, and C. We can come back up here and we can write this as equals 4 over x minus 1. I go, that equals 0. Plus, C was 16, right? Yep. Plus 16 over x minus 2 squared. And I should have had the integral symbol there. dx. Go over to blue. And so now this is something we're familiar with. You can use substitution if you don't feel comfortable with this portion. So this is 4 over x minus 1 dx. You can factor out the 4. 1 over x minus 1 integral dx. You say u equals x minus 1, du equals dx, and you're left with 4 integral 1 over u du, which equals 4 natural log of u, which equals 4 natural log x minus 1. So a lot of times, once you've done that a few times, you kind of just do it in your head, and you realize that that extra 1, negative 1 in there doesn't really matter, and it's the natural log. But for the first few times, it's sometimes nice to go through it step by step. And that's what's the absolute value, even though I wrote just normal brackets. And then we're going to have plus 16, and this is x minus 2 squared, so it's going to be 1 over x minus 1, 2. So we have x minus 2 to the negative second. It goes up a power. So you have x minus 2 to the negative first, and you divide by negative 1. So it then becomes negative 16. And so then our final answer is, and then we'll add in a c. So this is our final answer right here for this equation right here. And you might be thinking, well, is there an easier way to do this? And the answer is not really. Integrals can get overly complicated when it feels like they shouldn't be. So that's how you would solve this equation using partial fractions. And the clue that it's partial fractions is when you start seeing polynomials in the denominator like this, you know you can break it up into other parts. And that should be kind of your clue to, okay, this is going to be a partial fractions problem. Okay, I'm going to clean this board up and we'll go to another. And example number 2. So same idea here. We have x cubed in the bottom, x squared in the top, so we don't have to divide. And it looks like we have that polynomial to the k, so we'll just do a whole bunch of the bottom polynomials. So this will be a over x plus 1 plus b over x plus 1 squared plus c x plus 1 cubed. Okay? And then we will combine everything again back into one fraction. So we'll have x plus 1 squared. Yep. Plus b times x plus 1 plus c with no change. And this will all be over x plus 1 cubed. Okay? Then we'll expand things out a little bit. So we'll have a times x squared plus 2x. 2x. Does x? Does x. Getting too distracted. Too distracted. Need to focus. Plus c. All over x plus 1 cubed And then we're going to have x squared times a, that's convenient, draw a little bracket around it, plus x times 2a plus b plus 1 times a plus b plus c. Haha. And then we know that this is going to equal x squared minus x plus 1. Yep. So we know that a x squared equals x squared. Therefore, a equals 1. I'm going to do this in a slightly different format than the previous problem. There's lots of different ways you can basically just set this problem up so that you to logistically work through it. So here I'm saying that ax squared equals x squared over there. And similarly, I would look at this section right here and say that 2a plus b x equals negative 1 times x. X's cancel. Then we get 2a plus b equals negative 1. Change pen color. We know that a is 1. So 2 times 1 plus b equals negative 1. So 2 times 1 plus 1 equals b, which equals 3. I think that's supposed to be a plus there, which makes that a minus. So b equals negative 3. There we go. It is really easy to get turned around with these. Okay. And you make one small problem all over. Okay. Slightly bigger picture. Now we have a plus b plus c equals 1. And we know that a is 1, so we have 1 minus 3 plus c equals 1. C equals 1 minus 1 plus 3. This is 0, that's 3. So we have c equals 3. We have a equals 1. And so now we can go back to our more original equation. You can see how this is sort of paper intensive. This is probably the reason the rainforest is dying. Well, not this specific reason, because this is electrons. No one cares about electrons. Let's see, 1 over x plus 1 minus 3 times x plus 1 squared plus 3 over x plus 1 cubed. And then this is integral dx. I know my notation is terrible, so I'll change this to a arrow. So it says that they're related, but I don't want to specify why. 1, negative 3, 3. 1, negative 3. Yes. Okay. So now, off to the integration part. Whoop. Ooh, red. So we'll have natural log of x minus 1 minus, see if I can do this in my head, 3 times x plus 1 to the negative 1 all over negative 1 plus 3 times x plus 1 to the negative 2 all over negative 2. And this will give us natural log of, and I'll do absolute value signs, which I should have done the first time, but I didn't. 3, whoop, right over here, 3 over x plus 1, because the negatives cancel. 2 wrongs make a right. They don't actually make a right. Maybe they do. 3 lefts do. 3 lefts do make a right. There we go. That looks pretty good. And then we'll add on the constant, which I tend to forget, because everyone forgets it. And it's unimportant and, well, I guess it's important. Constants have feelings too. Okay, so that's the second example. Let's go for one more example, then we'll look at a AP style example. Okay, so now this one, on first thought, you think, okay, they had the same order. We're going to do the little division thing. Do we do the division thing? Yes. So your first thought might be, well, you can break this up into x squared minus 1 over x plus 4 over x minus 4, but then you still have the denominator, so you have the numerator then greater than denominator. So instead of breaking it up into x plus 4 and x minus 4, we'll start by dividing the numerator by the denominator. So the way we do that is long division. I think I learned long division in, what was it, 5th grade? 4th grade? No, I don't think. I just learned the multiplication tables in 3rd grade. Maybe it was like 7th. Either way, I did not appreciate how cool it actually was at the time. So you tend to forget skills that you don't use. And we never really did long division with variables like x. So it's a new skill if you haven't done it yet for a while. So I added in the 0x here because you can always add 0 in life, and you can always multiply by 1. So I'm adding 0x's here pretty much as a placeholder, so you don't forget that there's something there. So you look at the highest order, which is the x squared. So there's x squared here, x squared there. We can have 1. So then you multiply that 1 by this section right here. So this is the numerator. I know it's terribly written, but you know what it is. Denominator. Yeah, I purposely made that one extra bad, but you understand. 1 times x squared, we have x squared. 1 times 0 plus 0x. 1 times 16 is negative 16. So you multiply it out and then you subtract it. So I usually do it sort of like this. And then I distribute the negative. That way it kind of keeps everything clean. And you see that the x squared minus x squared is 0x squared. 0 minus 0 is 0x. And then negative 1 plus 16 will be 15. And so you write remainder 15 up here. I never quite understood what the remainder was for in life when I was younger. And now that I'm older and more mature, I have a better appreciation for it. So we can rewrite this equation right here as 1 plus 15 over x squared minus 16 dx. Whoop, integral. And now we can go for the difference of squares. Whoop. If you don't remember difference of squares, well, you should. You should remember everything in life, which is, that's a lot to ask for. Especially when you have a memory as small and puny as mine. Not an easy thing to ask for. Okay, focus, enough distraction. Actually, I'm just going to look at this portion right here. So we have 15 over x plus 4, x minus 4. And if you multiply these out, you'd see they get x squared minus 16. And this is a over x plus 4 plus b over x minus 4. Combining those together, we have a times x minus 4 plus b x plus 4. Okay, seems reasonable. Then, so we're going to have x times a plus b plus 1 times b 4b minus 4a. Okay, so 4b, 4a, okay. So we know that since we have 15 here, a plus b equals 0, which means that a equals negative b. And we have 4b minus 4a equals 15. And we'll replace the come on, pen, there we go. Ooh, maybe I should change the color. Oh no, that's too much, ooh, gray. I haven't used gray for a while. 4b, I don't like gray, that's why I did not use it, equals 15, positive, 8b equals 15, b equals 15 over 8, which since a equals negative b, a will be negative 15 over 8. Okay, yep, we're moving off of gray. Sorry, gray. You are dead to me. Okay, then try not to lose track. You can see we're a normal, non-infinite piece of paper. This would be more challenging. So we have 15 over x plus 4, x minus 4 equals negative 15 over 8 times 1 over x plus 4 plus 15 over 8. Yep, okay, we got this. Over 1 over x minus 4. Okay, and then I'm going to abuse notation a little bit, and I'm just going to throw in that extra 1 plus 1, do an integral sign, and now this is the same as our original because I added this part in. Okay, so now we can do this. So then zoom back in because this is all the information that I need. A little bit of tunnel vision, if you will. I'm going to do the 1 first because it's just easier. So I'm going to say x plus 15 over 8 natural log of x minus 4 minus 15 over 8 times natural log of x plus 4. And then there's probably a c in there, but I'll get to that in a sec. Equals x plus 15 over 8 natural log of x minus 4 over x plus 4 plus c. Yep, that looks like the right, feels like the right answer. And so then this would be our final answer for this problem. And on this problem, we used since the denominator was the same order as the numerator, we had to do long division first to take off the, we basically got a 1 on the side. And that was one of the last technique we used for partial fractions. Now let's do one more problem. I like the way I left the rules up there, but then I haven't used them at all. And I've been kind of zooming around too much for you to even really notice them. I have not been making this easy nor convenient for you. Okay, last example for the partial fractions. Ooh, interesting. Teal, green. I like green. I haven't done green for a while. Okay, so we have this up here and that down there, and we're going to say, ooh, maybe I can zoom in and just, okay. I'm gonna have to do some small writing here. Equals 0 to 1, 5x plus 8. Maybe a little bit slower, a little bit more controlled. X plus 1 times x plus 2. Does that look good? 2 plus 1, 3. Yep, I'm good with this. Equals, ooh. You should take up more space when you actually do this. But I saw the opportunity and I was like, you know, I'm going to take that terrible opportunity and I'm going to run with it. Might not be a good idea, but at least it's an idea. And then there's still supposed to be a dx. A times x plus 2 plus b times x plus 1 all over x plus 1 times x plus 2 equals x times, what's it, a plus b? A plus b plus 1 times 2a plus b all over x plus 1 times x plus 2. And then change color, go to magenta, look at our original. So this cancels and that cancels. And then we have a plus b equals 5. And we have 2a plus b equals 8. And let's see here. So then if we do, we could do, no. Keep it simple and just do substitution. A equals 5 minus b. So 2 times a is just 2 times 5 minus b. Plus b equals 8. So 10 minus b equals 8. Negative b equals negative 2. B equals 2. A equals 5 minus 2. A equals 3. Except that looks like an R. I know you guys don't care, but I care, and it bothers me, and it hurts my soul. There we go. 2. A equals 3, B equals 2. Remember. So, rewriting everything. I already forgot. A equals 3. Yep. 3 times x plus 1 plus 2 over x plus 2 dx. Oh, okay. And then we solve this out. We have 3 natural log of x plus 1 times plus, I meant plus 3, and these are absolute value signs. These are not, those are brackets, not absolute value signs, but they should be absolute value signs. If I was a better math guy, they would be absolute value signs, but alas, I am not. I think it's from 0 to 1. 0 to 1, okay. So now we're going to plug in both 0 and 1. That's a little, it's fine. Okay, so now I'll have 3 times the natural log of 2 plus 2 times the natural log of 3. I kind of like that. It's kind of very zenful, very balanced. I like the symmetry. Minus 3 natural log of 1 minus 2 natural log of 2. Add some contrast. Natural log of 1 is 0. If you don't believe me, you can put it in your calculator. Actually, I really don't believe me. I'm going to put it in my calculator. Whoop. And natural log of 1 is 0. And if you take the natural log of 0, the world should end. Yep, end of the world. Negative infinity. Okay. So then we have, let's see here. Focus. 2 natural log of 2, 3 natural log. So we have natural log of 1 natural log of 2 plus 2 natural log of 3, which is, let's see what our answers are. Nope. Okay. Let's do some more mathematical magic. Natural log of 2, that's about as simple as that gets. But we can have natural log of 3 squared, which is 9. And then we can combine these as natural log of 2 times 9, which is natural log of 18. And we don't need a c because this is a this has limits of integration. So, yep, right there. There it is. So natural log of 18. And then divergent. Divergent means it equals infinity. If this equaled infinity, then it would be divergent. Or I think also probably if it equaled negative infinity, it would also be divergent. So that's what the divergent means, and the others are just wrong. I don't know how you get those. They all look semi-plausible, but they're not. Natural log of 18 is the answer. And that is the concept of how you do partial fractions. If you see an ax plus b, you use an a. Ax plus b to a exponent, then you have to include all the polynomials leading up to your k. And then if you see a quadratic on the bottom, which we didn't do, but same concept, ax squared plus bx plus c, then you have to have ax plus b in the numerator. And then you solve it the same way using algebra. So this is another technique you can use for integration. It doesn't come up that often, but it's good to be able to do it and just have a general idea that it exists, because once you know to look for it, then you can just kind of churn through the math. So, sounds good. I appreciate you guys joining me, and I will see you next time.